Hello, everyone, and welcome to another great day of chemistry. So, last time we finished up talking about compression and expansion of ideal gases and how we can use this to really identify the work of a system. So, this time we're going to actually flip to constant volume conditions so we can really nail down a good definition of heat. So far we know that the change of energy in a system is going to be related to the amount of heat and work entering the system. So, this is our first law definition where the overall change in energy is just going to be the sum of the energy coming in as work or as heat. Now we have a good definition of work. So work is going to mostly take place as this PV work, where it's going to be based on the external pressure and how much that causes the volume to a change, whether the work is entering the system, if it's being compressed, or exiting the system under an expansion. But what this doesn't end up addressing is the heat. So one of the things that we can often do with these path functions is if we can go ahead and constrain our work, this will make it much easier to determine the heat of the system. So what conditions are we going to find the work being really simple? Well, so far we've seen two easy cases. One, we set the external pressure to zero, but then we have an expansion, and that's tricky. The other one, we can go ahead and say, well, what if the volume doesn't change? So if we have a fixed volume condition, the volume won't change, and that means that there will be no work accomplished because work is always about movement against a force. So we can control the force or we can control the movement. Well, the easiest case is we don't let the system move. Now at this point we get really lucky because now our change in internal energy is equal to the change in heat. By constraining the system, I'm able to turn heat from a state function or from a path function into a state function. Or in discrete terms, the heat is just going to be the same as the change in internal energy. So now if we can identify one, we should be able to identify the other. And so one of the things is this also lets us kind of rethink how we think about the internal energy. Because we can also think about changes in internal energy as how much heat it would take to change the system under constant volume conditions. So in order to look at this, we're going to need to be able to measure an increase in energy in an isochoric system, which means we now need to take another look at our state functions for internal energy. Now, this is where having an ideal gas is going to be really useful because if I'm heating an ideal gas, where can all that energy go? Well, we don't have any potential energy, so that means it's all pretty much going to have to go into kinetic energy. The dominant form of kinetic energy is going to be temperature. So for an ideal gas, as we increase the temperature, we increase the internal energy. And it turns out we can show that this is going to be proportional, which means we can relate these with a constant. And CV here is going to stand for the isochoric heat capacity. So we're going to have a lot of subscripts showing up in our variables here. If I have a subscript of a V, that means we're holding V constant. So CV is simply just going to be the heat capacity under constant volume conditions. And this means that if I'm able to determine this parameter, I can go ahead and relate changes in temperature to changes in internal energy. So this is going to be really useful. But note, this is an infinitesimal stance. So we can go ahead and turn this into a discrete variable by taking the integral of CV dt. Now here, if we assume that the isochoric heat capacity has no temperature dependence, the integral actually occurs fairly nice, and we just get CV delta T. But note, this does count on the fact that this is a temperature independent constant. And we'll address that later. So again, what is this CV? Now we have the classic calculus circular logic. The isochoric heat capacity is just going to literally be how much does the internal energy change with respect to temperature under constant volume. Of course it does. But what we need is going to be a temperature dependent expression for the internal energy. Because if I know how the internal energy changes with temperature, then I can just simply take the derivative to get my heat capacity. Now, it is worth noting that This is going to take many different forms for many different substances. But since we're still focusing in on that ideal gas, now we get really lucky because I said all of this energy is going to be the kinetic energy. And it's almost like we were able to derive an expression for the kinetic energy of an ideal gas in the last chapter. So we found last chapter that for a monatomic gas, we have 1/2 kT of energy for every degree of motion. That means if we put it into a discrete basis, it's going to be with 3 degrees of motion, 3/2 kT. Then we're going to turn this into nr again. So we know the moles, and then we replace the Boltzmann constant with the gas constant. So for a monatomic gas, this means our internal energy is 3/2 nRT. Beautiful. I know how much gas I have. I know the temperature. I know the internal energy due to kinetic motion. It's beautiful. But here's the nice bit, that if I take the derivative with respect to temperature, I get the heat capacity, which turns out gives us a heat capacity of 3/2 nR. So for any monatomic gas, so this is really useful for our noble gases, we have our heat capacity. But we can also repeat the system for the diatomic gas, which again, if you remember, have 3 degrees of translation and 2 degrees of rotation. So that's 5 degrees. So this has an internal energy of 5/2 nRT and a heat capacity of 5/2 nR. And it's worth noting, this actually works fairly well for a lot of our common ideal gases. They are very close to this number. So that's things like oxygen and nitrogen. So air. So this is again really useful. However, there are many gases that are much more complex. So for a nonlinear system, we have 3 degrees of translation and 3 degrees of rotation. That gives us 6/2 or 3 nRT. The problem is we have these vibrational motions, which add a little bit of extra energy, not a full extra half kT, but enough so that we have a bottom limit for all of our other gases. But unfortunately, we have to determine the actual value experimentally, which we'll talk a little bit more about next time. So this also gives us a bottom limit for our isochoric heat capacity. So again, very useful. So now we can go ahead and look at the temperature dependence of these systems. So our heat capacity is going to be based on that change in energy with respect to temperature. And we know that that's going to be that change in energy is going to be related to the heat. So if I get one, I should be able to get the other. Now, one of the things we have to watch out is for most chemical systems, it turns out that that CV actually has a little bit of a temperature dependency. Because of course it does, which means we don't get that simple delta T expression. We have to actually take the integral. Because it turns out for most systems, we have a curvilinear relationship, where you can think of this as a very gently sloping exponential, where the heat capacity is going to be much higher at higher temperatures and lower at lower temperatures. Which means that in practice, if I'm going to determine the heat capacity, I need to do it for the experimentally relevant temperature, or I need to find a value for that temperature in the literature. Now here we can take advantage that this heat capacity does change relatively slowly. So we often consider the heat capacity fixed for about 100 degrees. If you're doing higher precision measurements, you might need to find a more complete expression. But generally, if you find a heat capacity for 25 degrees Celsius, that will work generally in the 0 to 100 range, but don't try and use it for 200 degrees C. So let's take a look at what we found so far. So far, we now have our first law, which relates the changes in internal energy to heat and work. And we know that work is going to depend on the external pressure and the changes in volume. Now, here's the useful thing. Because when we constrained our heat deriving our internal energy, we find the internal energy is equal to that CV delta T, but notice on both sides, these are all state functions, which means even though we derive this based on an isochoric heat, this relationship will always be true. Caveat for an ideal system. But for an ideal system, if you know the change in temperature and you've determined that isochoric heat capacity, you know the internal energy. And that's really useful even if you're looking at a non-isochoric system. And again, we can do this based on just taking the integral of the CV delta T. So again, note that this internal energy, CV delta T, is only equal to the heat if we're under isochoric conditions. It will always be equal to the internal energy, but only equal to heat under isochoric conditions, not under any other. So next time, we're going to actually dive in a little bit more on how we can determine these CVs. So how can we look at these isochoric heat capacities, as well as our first look at reactions as we talk about bomb calorimetry. Until then, take care.